All right, so let's apply Taylor's theorem to a few specific functions to kind of see what it looks like in some different cases to be able to prove that some familiar functions have Taylor series which actually represent them on some interval, so that the Taylor series actually converge to the correct value, basically. Okay, so for the very first one, let's look at f of x equals e to the x, right? Then let's say by fiat, right? We haven't actually shown anything. We haven't actually defined e to the x. So, but we can let's just assume that we know that all the derivatives of f of x are just e to the x, right? So fn of x equals e to the x for all n and for all x in R. So fn of 0 is just 1 for all n, right? So the Taylor series of f about 0 is the sum of 1 over k factorial x to the k, as we've seen before, right? So now note that for, let's say, for any m greater than 0, we have that fn of x is less than, let's say, absolute value of fn of x is less than e to the m for all n and for all x. So this is for all n in n and for all x in negative m. So corollary, what was it? Corollary 31.4, the one we just proved, right? Shows that Rn of x goes to 0 for all x in negative m. Right, and that shows that so the Taylor series converges to e to the x for any x in R, right? And the reason that we can say from this that it converges for any x in R is that if you fix a value of x in R beforehand, then all you have to do is choose some capital M bigger than the absolute value of x. So that way x is actually in the open interval from negative m to m. And then you apply this argument on that open interval, right? And that shows that Rn of x goes to 0, which means that the Taylor series converges to e to the x for that value of x, right? So it's actually kind of a similar pattern of logic to like how we showed that power series converge uniformly, like that a power series is continuous on the interior of its interval of convergence, even if the convergence isn't uniform on the entire interval, because on any smaller closed interval, the convergence is uniform. So if you fix any value, if you fix any point in the overall interval of convergence, then you just make a slightly bigger closed interval that contains that point, and then the convergence is uniform, so the function is continuous to that point, right? It's the same like pattern. So anyway, that's e to the x. Let's look at another. So let's say f of x is sine of x. Then, so fn of x, as we know, is sine of x for n equals 0 for 8, so on. Cosine of x for n equals 1, 5, 9, and so on. Negative sine of x for n equals 2, 6, 10, and so on. And negative cosine of x for n equals 3, 7, 11, and so on. Right? So Fn of 0 is, and it can be grouped into, so if n is even, then Fn of 0 is just 0. And if n is odd, then Fn of 0 alternates between being plus or minus 1, right? Right, so what we can say is that Fn of 0 is 0 if n equals 2k, right? Some k greater than equal to 0, k in Z. And -1 to, let's see, so it should be +1 when n is 1. So yeah, to the k if n equals 2k plus 1 for some k greater than or equal to 0, k in Z, right? Okay. So then the Taylor series, right? Is the series from k equals 0 to infinity. And so we can just, since all the even powers of x, or all the even numbered derivatives of f are 0, we can just form the Taylor series by running through the odd number terms. So we can index by k here, and we can use -1 to the k over 2k plus 1 factorial x to the 2k plus 1. Yeah. So, and also note that Fn of x is just like less than or equal to 1 for all n and for all x in R. So the Taylor series converges to sine of x for all x in R. That's again by corollary 31.4. Yeah. So anyway, so those are two kind of like pretty simple examples. Let's do one more here. So and I'm gonna do this. So in this example in the book, they just use it to prove that like the alternating series of 1 over n, -1 to the n over n, converges to log of 2. And I'm just going to prove that the power series converges for like, well, yeah, I mean, we'll see. Yeah, so say f of x equals log of 1 plus x. Then f prime of x equals, this is for x in -1, infinity. So f prime of x is 1 over 1 plus x. F double prime of x is -1 over 1 plus x squared. F triple prime of x is 2 over 1 plus x cubed. F4 of x is -3 times 2 over 1 plus x to the 4th. And so you can see the pattern is, right, each time we multiply by the next number. So we're building up like, n-1 factorial on top. And then the sign is also alternating. So Fn of x we can write in general as -1 to the n plus 1 times right, n minus 1 factorial 1 plus x, or x plus, yeah, 1 plus x to the negative n. This is for n greater than 0, right? So, so for n greater than 0, fn of 0 is -1 to the n plus 1, n minus 1 factorial, okay? So the Taylor series of f about 0 is the sum from k equals 0 to infinity of, well, actually the sum from k equals 1. Let's just, for convenience, start from k equals 1, because f of 0 is just 0. So the first term in the Taylor series is just automatically 0. So we can start from k equals 1, and then we'll get so -1 to the k plus 1, k minus 1 factorial over k factorial, x to the k, which is the sum of -1 to the k plus 1 over k factorial, or not k factorial, sorry, because the k minus 1 factorial cancels out with a bunch of the k factorial, leaves only k left, x to the k, right? So we've kind of seen this before, but now you can see how we can arrive at this series from considering the derivatives of f, right? Now that we understand the relationship between the derivatives of f and the coefficients in the power series representation, we can sort of derive the Taylor series of f that way, right? And then, so if we fix 0, let's say 0 less than or equal to, well, yeah, let's say 0 less than x less than 1, or less than or equal to 1. Okay. Then, right, okay, sorry. So I was just checking something in the notes again. Yeah, so if we fix a value of x like this, then, Taylor's theorem tells us that for each n, there exists a yn in 0x such that Rn of x equals Fn of yn over n factorial x to the n, right? So now Fn of yn is just going to be this is negative, right? We can use the formula, right? So this is -1 to the n plus 1, n minus 1 factorial, 1 plus yn to the negative n over n factorial x to the n. And then this is, sorry, this is an n factorial. Then this is -1 to the n plus 1, x to the n over n times 1 plus yn to the n, right? And as you can see, so Rn of x equals just, well, it just equals x to the n over n times 1 plus yn to the n. And this goes to 0 as n goes to infinity, right? Since, you know, x is less than or equal to 1. So this is, right, maybe what I could say, maybe what would be better to say is that this is less than or equal to 1 over n 1 plus yn to the n. And this goes to 0 since yn is greater than 0, right? So so this means that Rn of x goes to 0 as n goes to infinity for 0 less than x less than or equal to 1, meaning the Taylor series sum from k equals 1 to infinity, negative 1 to the k plus 1 over k x to the k converges to log 1 plus x on 0, 1. Of course, one can also show it converges to f of x on negative 1, 0, or I mean, whatever. It doesn't. At 0, it's obvious that it equals f of x, but yeah, you can show that it also works on this other part of the domain, but I'm not really interested in that right now. So in particular, for x equals 1, we have that the series of negative 1 to the k plus 1 over k from k equals 1 to infinity equals log of 2, right? But we actually showed the way I phrased the argument, and it's not that much different from what's in the book. You just end up with this x to the n here, which doesn't really do anything. But the way I went about this ends up showing that actually the Taylor series of this function converges to the function itself on all of these points on this interval. And in fact, you can probably, without too much difficulty, you can prove a general theorem that, like, if the Taylor series converges to f of x at a certain point away from the center, then like at all the points in between, it should also converge to f of x. So like just showing that the Taylor series converges to log of 2 when x is 1 should be enough by some extra reasoning, which I'm not going to get bogged down in right now. But there's probably some extra reasoning that you could come up with in general that would let you then argue that since it converges at x equals 1, it also converges at all of the values between 0 and 1. Specifically that it converges to log of 1 plus x at those values. I think that should work. In fact, you could probably even extend that to prove, like, if it converges at x at like an endpoint of the interval of convergence of this power series, then it should, if it converges to f of x at an endpoint of the interval at an endpoint of the interval of convergence, then it should converge to f of x on the whole interval of convergence, I think. But anyway, so for now, let's just be content with this. So you can see how Taylor's theorem is very nice. It's very useful for proving convergence of Taylor series. So in the next video, we will actually, in the next video, I'm going to go through an example of a function which has all of its derivatives at 0, but does not have a Taylor, or whose Taylor series does not converge to the actual function. So kind of a weird pathological function. And then we'll look at an integral form of Taylor's theorem.